So I just wanted to tell you this. We're forming the competition team now. We haven't done this for a year or so. Now we're finally back. So email Elizabeth to get on the team. This is extremely useful to students. All the students that have competed on these teams, almost all of them have walked into very good jobs. So they'll do some of these events. It's not exactly clear which events we're going to do. That's going to depend, I guess, on who's on the team and what the deadlines are and stuff. But in the past, we participated in the CPTC and the CCDC. Those are really famous competitions that have regional and nationwide versions. And there's also the National Cyber League, which we may do. And there are other ones, too. We've done quite a few other ones. So I highly recommend anybody who's interested in moving beyond our classes to closer to the industry level of competence to do this. This is how you really get the hands-on experience and the exposure to a higher degree of difficulty, and you impress people and often get good jobs. Is there a restriction if you already graduated? For some of these there is, and for some of them there isn't. That's why I put this here. Full-time and part-time students can compete. I know, for example, CCDC has some events called practice events or something where anybody can participate. You don't have to be a student at all. Then there's a big one where they model after football, where you absolutely have to be a full-time student and everything. But there's some that require that and some that don't. So you should apply if you're interested, and there'll be something for you to do. And this is really very good for the students. They get very competitive. They try really hard to win, and it motivates them to move forward. By the way, it doesn't matter if you win. Nobody cares when I say that, but winning just helps the college. It doesn't really matter to the students. People will hire you whether you win or lose. The fact that you're on these national teams means you're in the top 1%. They snap them up. They don't care whether you won or not. But anyway, the students do compete very hard, and that keeps them working. They learn a lot more than you'd learn in the classes. Well, for you're going to learn security. You learn in pen testing, you're going to learn attack, and in defense team, you're going to learn defense. And I think in NCL, you learn sort of security plus level general skills in security. But they're all in this field. And
what's the time commitment?
I don't know. I think in the past they had like 1 or 2 evenings a week they practiced, and they organized it, but that's all being organized now. I would inquire, because I think they're still working it out. We had an established team, but then we had no team for a year or so, and most of those people have graduated, so now we're forming a new team, and it'll take a while. Anyway, I highly recommend contacting Elizabeth and checking it out. All right. Anyway, so let's talk about cryptography. We're down to randomness today, which is here. All right, and I should have that open somewhere. All right. So, randomness is in fact a really, really big issue in cryptography. It might seem silly, but you need random numbers, and you need high quality random numbers, and they're not easily come by. So we'll talk about randomness and how it's created and how you measure it and how it goes wrong. And so Dilbert has a cartoon for everything. So he has a random number generator that gives you 999,999. And now the question, is that random? How do you know? It could be random. You could get that many 9s in a row, or maybe it's not. And that's the problem. So can a capture card for gaming work for this situation? I'm afraid I do not know what you're talking about. Zhu?
Competition.
Capture card for gaming? No, he's talking about some kind of hardware for a video card, and I do not know. You're talking about as a source of randomness? You'll have to give me more information. I'm baffled by that question. Anyway, GPU. Yeah, well, I'll wait for hopefully the other students can figure out what you're talking about there. Anyway, so this looks more random than that to a casual observer, but of course, if this is the exact series of bits, it's no more likely than that. The point is, though, when people look at that, they summarize it like 3 zeros and 5 ones. And if that was your description, then there would be many patterns of bits that satisfy that description, and then it would be more likely. And this is essentially what the law of entropy is. It's there are many more disordered states than ordered states, so things are more likely to progress into a state of disorder because the word disorder describes a larger category. So this is beginning to get into the issue of what randomness is. So you can see it as a probability distribution. A fair coin has 50% chance of head, 50% chance of tails. Dice has a 1/6 chance of each of the 6 faces. That's a uniform distribution. That's what you often want, although it's not the only kind of randomness. So you measure it with entropy. And this is Shannon's entropy, which is also called information content. This was a big breakthrough. So if you have a distribution of n possibilities, and each one of them has a probability of p, so all these will add up to 1, then you calculate p log p, p2 log 2, pn log n, and since the probabilities are less than 1, all the logs are negative, so you take the minus sign and add them up, and take the logs to the base 2, and now you have a number that we call Shannon entropy, or information content, and it's that way because it nicely matches bits. So if I have one random bit that has a 1/2 chance of being 0 and a 1/2 chance of being 1, then the entropy is minus 1/2 log a half minus a half log a half. Log of this is minus 1, because the log of 2 is 1, log of 1 is 0, and log of 1/2 is minus 1. So this is 1. That's why you call it. So if you have one bit that had an equal chance of being 1 or 0, it has an information content of 1 bit. If I have a random byte, there are 256 possible values. So you take minus 1 256 of log 1 256. This is minus 8. So you get 256 terms, each of them being 8 times 1 over 256. So you get 8 bits. So it matches your intuition. If you have one byte that could be any possible value, it contains 8 bits of information, just like it should. Yeah?
Entropy is not about bits, right? It's just a measure of randomness.
It is. That's right. But you can interpret it as the information content in bits. This is what Shannon figured out. And that's why if you have a document, for example, that a whole bunch, like a Microsoft Word document, has a whole lot of zeros in it. Many of the bytes are zeros, so it's not full. So you can squish it with, say, WinZip and make it smaller, and then the bits will appear random. So a document that is repetitive has less information in it. So if you have, a 20 kilobyte Word document, but most of the bytes are 0, it does not contain 20 kilobytes of information. You can zip it down to maybe 5 kilobytes. That's how much information is in there. And that's the point. So if you zip it down, then you'll explore all values of the byte, and then it can't be any. That's how you squeeze the air out of a file to make it smaller. So that's right. It's a measure of disorder, but the maximum disordered state has the most information. An ordered state, like all the bytes the same, contains almost no information. You can describe that file by just saying every byte is 0. So it contains almost nothing. And that's the point here. So if one non-random bit, you'll get a probability of 1 for one outcome and a 0 for the other, so the entropy is 0. If there isn't any variation in the data, then the entropy is 0 and the information content is 0. And so you can do this with Python if you like. You can import math and do math.log to the base 2 and add them up. So here's a fair coin with 50-50, so you get an entropy of 1. You can make a 8 option thing, a thing that has 8 possibilities, each with probability of 1/8, and then you'll again get an entropy of 3. That's 3 bits. And you can have an unfair coin with a 90% chance of 0 and a 10% chance of 1, and then the entropy is about half a bit. So that's how you quantify the entropy, which is a measure of the information content. Someone would like to compete. Good. I see people bringing it up. Good. All right. Good. All right, so let's take a look at a Kahoot. Let's see if I'm going to get my stuff working here. All right. Yes. There we go. No, that's not what I wanted. There's no back button. I'm somewhere stupid. Okay, here we go. 141 2A, that sounds about right. Okay. There we go. All right. Well, maybe that's it. Maybe not. Okay, I'll wait a bit. Combining videos and streaming only. I don't know anything about all that stuff they're talking about. Oh, anyway. All right. All right, so what is that? Log of 1/4 to the base 2. Yep, -2. Good, because it's 2 to the -2. All right, what's the entropy of 1 bit? That is random. It has 1 bit of information. All right, how about a random byte? All right, that's 8 bits. All right. How about a random base 64 character? Yeah, that's 6 bits. 6 bits in a base 64 character. All right, good. Hey, I don't know who that is. They'll have to tell me who they are if they want the points. PB. And LC sounds like enough of an initial. My brother will probably figure it out. But the horse faces, we will not figure it out. All right, anyway. So, all right. All right, so let's talk about random number generators. There's 2 kinds, random number generators and pseudo-random number generators. Now, so you need real entropy. This is a problem with computers. In computers, there's really nothing that is intended to be uncontrolled or unpredictable. It's all supposed to be following an algorithm, so that's a problem. So real entropy comes from random number generator, and then once you have some randomness that came from something actually random, then you can use a pseudo-random number generator to generate more random-looking bits from it. So a real random number generator, you need a source of something that really varies, like temperature, acoustic noise, key presses, something in the real physical world that's really random. So that's, of course, a problem with computers that may not have that, although, as we'll see, some modern computers do, in fact, have hardware random number generators. And then you can have a quantum random noise generator is one way to do it, where you'd have a quantum occurrence like radioactive decay or the random motion of atoms or light, and you use that as the source of randomness, which is fine if you have access to something like that, some kind of sensor that will pick up some randomly fluctuating object. Then you have the pseudo-random generator, which takes a few truly random bits and creates many artificial random bits from it. So your random number generator measures some actual physical thing that's moving, and it gets some bits out of that, but probably not too many. So then you use a pseudo-random number generator to use that as a seed to create a long chain of simulated random bits that are not perfectly random, but they're random enough for most purposes, as long as you have some entropy here. So the pseudo-random number generator just harvests random bits from the real random number generator, and it uses that to update an entropy pool, and it uses the entropy pool as sort of a seed to just calculate a series of pseudo-random values. And we'll go into quite a bit of detail. In fact, a lot of these work by using encryption algorithms, which we'll talk about. In a sense, that's what an encryption algorithm is. You have a key, and you create a repeatable pattern of random-looking bits from it, and then use those bits to encrypt the data. That's how quite a few of the secret key algorithms work. So it uses a deterministic random bit generator, which just creates a long sequence of numbers that depend in a non-obvious way on the entropy it got from the entropy pool. But if you give it the same input again, you'll get exactly the same stream of bits. It's not really random. It just depends on the seed. So you have an initialization operation that will initialize the entropy pool. You have a refresh operation that will reseed it by drawing fresh random bits from the real random source. And you can go to the next, which will just give you more pseudo-random bits. All right, this gives you forward secrecy, a big issue these days. Forward secrecy hit the news because of Edward Snowden. The question is, if I encrypt stuff and send it over the internet, what about next year? Maybe next year somebody will put malware on my computer and steal the secret key, and then they'll be able to decrypt my previously encrypted stuff. If you don't want that to happen, you want a cryptographic system with this property, forward secrecy, which means that you cannot, every session is unique. So if you connect tomorrow, the key is not predictable from what was known before. That's called forward secrecy. You cannot go back in time and decrypt stuff later by stealing the key later. And this is backtracking resistance, or forward secrecy. Another desirable property is prediction resistance, for even if I measure all the random numbers for a long time, I cannot calculate from them what the coming random numbers are going to be. You don't want either of those to be possible. You don't want to be able to take a sequence and go back in time, or take a sequence and go forward in time. Yeah?
And, so I read the book, and it was talking about using like quantum events or electrical noise.
Yeah.
But I wonder if there's something in the area of fractal mathematics that it can model very bursty noise or noise patterns, and then it becomes deterministic because it's a repetitive pattern that is found in nature.
Well, yeah, and that's right. So, I mean, they are in fact using that kind of algorithm as their pseudo-random number generator, so they avoid it repeating, but it's similar kind of mathematics.
Yeah.
And fractals, you're right, that's why it would not pass these tests if it had some kind of repeating property.
Right.
You'd be able to predict something. That's where you lead to the gambler's fallacy, right? I've got 10 zeros, so the next one must be 1. And if it had some kind of rhythm or pattern, that would be true, and you don't want that to be true. No matter what pattern you see, you cannot deduce the future from it if you want to have these properties.
So, and I had a thought that I put in one of the comments, is
Yeah.
that the decimal expansion of pi is a transcendental number, so it's not a polynomial expansion or anything.
Right.
I wonder if you could if you have a long enough string of pi bits, and you randomly select where you're going to start. If it's less than 4, it's a 0. If it's 5 or greater, it's a 1.
Yeah, there's a company that just did this. There's a company called Crown Sterling, which claims that they have a whole new bunch of cryptography based on using those as a random stream.
Transcendental numbers.
Using transcendental numbers, and they are being totally excoriated by all the professional cryptographers saying you can't do that. They gave a presentation at Black Hat. They keep making these cryptographic claims that professional cryptographers do not respect. But they tried to do that. They tried to use transcendental numbers expanded in decimal as a source of like pseudo-random numbers. Apparently, it's not a good idea, but I don't know exactly why. But the professional cryptographers are not amused at all. Anyway, good. There's several random number generators. Good. See, someone's got a link there on Amazon.com. Yes, there are random number hardware products out there. Anyway, the reason why everyone cared about forward secrecy is because of the NSA. And the NSA is seriously doing it. They built this gigantic Utah data center, and they are capturing all the data they can and storing it for years in the hopes, because eventually, later, they managed to find some of the keys and they managed to decrypt it, and therefore they can find terrorist plots and child porn and all kinds of good stuff in there. And this made people nervous. And there it is, the Utah data center, storing all this data, waiting for keys to come in later. So it is a big issue, a failure of forward secrecy. And that's why everyone jumped up to TLS 1.2 and 1.3 on the internet, which do have forward secrecy. Every time you connect, they don't just take the public key that comes from the server, they create a new session key for every session. So you cannot decrypt yesterday's traffic with tomorrow's key.
Yeah.
But you could in TLS 1.1. So it made sense for the NSA to archive all that stuff. And it was because of Edward Snowden that everybody moved forward and updated to the new system. Until Snowden dumped all that stuff, everybody said, oh, who cares? That's just a theoretical attack. It doesn't really matter.
If you're a criminal, I guess you want forward resistance out to the statute of limitations.
Yes, logically, yes. But really, if you're anybody, you don't want your medical records getting out, your social security number, your password, Yeah. All right. So anyway, to achieve this, these operations must be irreversible. So even if the attacker had changed the entropy pool, they can't determine the bits. And you must refresh with fresh random numbers so that you make the future unpredictable. Because of course, if you didn't reseed it, then it would eventually have a pattern or repeat. So, all right. So Fortuna is one designed by Bruce Schneier, who's a very famous cryptographer, and another guy. And this is what Windows uses: 32 entropy pools, 16 bytes for the key, and 16 bytes for the counter. That's Windows that's Windows random number generator. Mac uses Yarrow, also made by a team including Schneier. If the random number generator does not produce enough random bits because whatever connection it has to some real object that's waving around isn't fast enough, then you have a problem. Now, Fortuna might produce lower quality bits or stop delivering bits. You can make a choice. Now, if you were actually able to fill the whole seed with the same seed values again, you'd get the identical sequence of bits. All right, so most pseudo-random number generators are called non-cryptographic. They have statistical randomness in that every bit is an equal chance of being 1 or 0, but they're not avoiding predictability. And they often use the Mersenne twister, which is one of the fractal algorithms you're talking about. But a cryptographic random number generator has the ability of being unpredictable. There is no pattern. So in the real world, devrandom is the Unix function that gets data from the crypto random number generator, and it's non-blocking. It always gives you bits, even if the entropy is low. It will still proceed. The original one people preferred was devrandom because this will block. It will not give you data unless the entropy is high enough. At first they thought this was a good idea, and then they found out, of course, when it doesn't give you random numbers, unless you remember to check for that, you're just going to get a series of zeros or something and be predictable. So in practice, they say it turned out not to be a good idea to block it, and they say use the one that always gives you the best randomness it can. This is a better practice than using the one that's going to refuse to give you bits, saying you have to wait until I get more randomness from the universe. Is Utah a good place for cheap, abundant electrical energy? I think it is, yes. I also land. Also, a lot of FBI agents and stuff. Yeah. So I think the government just found that to be a really natural place to put like a national security warehouse. And so this happened to me. I had a hacking server with practice things on it, and it ran Tomcat, and it took 45 minutes to reboot. And I couldn't believe it, and I Googled for it. And this is because when Tomcat boots up, it has to generate some random numbers to make a cryptographic key, and if you just have a headless server with no keyboard and no mouse, there's no randomness. So it takes 45 minutes for it to find any random bits, so you have to install this thing called havged, which creates more randomness on your server. And then it will boot up in like a few seconds. It's amazing. I didn't know that was even possible, but you can totally see it. And so I haven't set up a Linux machine to demonstrate this live, but it's kind of fun. You can do this. This is what will just print out the entropy available. And you can then just consume entropy by just taking, drawing data from devrandom. And when you do, you can see what it does. When I start, the pool is like 2,000, and when I start drawing data, it falls down rapidly to almost 0 and stays really low. You can easily print out enough. These random base 64 stuff being printed out is enough to use up all the available entropy, and there is no more available entropy in the pool. It doesn't fill up quickly. But if you install havged, it stays high all the time. It just creates a lot more random bits. It is software, though, so I suppose in principle those bits can't be perfectly random. But anyway, it fills up the pool a lot faster, so you don't run out of entropy. Anyway, in Windows, they had this crypt gen random. Now it's bcrypt gen random. And this takes entropy from the kernel mode driver. And I don't know exactly where it gets it in general in Windows. Intel decided to fix this in 2012 by putting hardware random number generator in the chip. Now that should be something like just a resistor running current, and then it multiplies the Johnson noise in the resistor, something like that. But because, again, of the Snowden revelations largely, although the other ones like it, people were worried that it might have a backdoor. How would you ever know? Poisoning the random number generator is considered the best way to achieve the goal of the national security community. The NSA has a goal called no bus. They want to have a backdoor into your encryption that nobody but us can use. And I heard someone, I think it was Bruce Schneier at a conference talking about this. He said if you wanted to achieve that, the best way to do it would be to poison the random number generator. So you could predict the random numbers. Nobody would ever figure that out. It wouldn't be obvious. And if you could do that, then you could get in and nobody else could. It would be a pretty good way to do it. But the problem is they might find out, whatever the secret is. And this has happened many times. That's why people are, in fact, very, very worried. If you don't know that those numbers are random, you can't audit them, you can't tell from the pattern, how do you know that somebody else doesn't know those random numbers? Unless you build your own hardware or something, it's really not obvious. So, and the problem, this is one of the big scandals that led to this, was this elliptic curve encryption scheme being pushed, and it was Microsoft researchers that figured this out in 2007. They said they're not claiming that NIST intentionally put a backdoor in it, but what they are saying is the prediction resistance of it is dependent on solving one instance of the elliptic curve discrete logarithm problem, which we'll talk a lot more about later, and you'll be solving problems like that. And the problem is that means it could be that they designed it knowing the answer to that problem. Discrete logarithm problem, they could choose a problem they know the answer to and use that as the standard because they tell you to use certain constants and they don't explain where they came from. So if you use those constants, you might very well be creating numbers which the NSA can predict because they know the secret numbers that led to it. And that's a problem. Also, it ran 1,000 times slower than the other options. And the NSA paid $1 million to Cisco to make it their default algorithm in hardware anyway. So it looks suspicious as hell. It really looks like they were pushing it on people, knowing it was a bad algorithm, knowing they could get in, trying to make it the standard. So Bruce Schneier said people should avoid it. And if this is part of the Snowden documents that leaked out, showing that the government did have a program in order to weaken encryption, using a variety of methods to pressure private companies and research companies into choosing insecure algorithms that they could hack their way into. And down here they say the SIGINT Enabling Project actively encourages U.S. and foreign IT industries to covertly influence their product designs, to use stuff we can hack into, insert vulnerabilities into commercial encryption systems, influence policies, standards, and so on. So they really do try to pressure people into using unsafe stuff so they can hack in. And of course, from their point of view, that makes it more safe because now the government can monitor you and stop it from being used for crime. This is the huge privacy battle that we're all living through all the time. The government wants to spy on everything, and the privacy advocates want the government to spy on nothing, and we end up with a constant tug of war here. So anyway, NIST formally removed that random number generator that appeared to be tainted. It's no longer part of the standard. It's no longer recommended. And so there are other ways things can go wrong besides people deliberately poisoning the system. Netscape in '96 tried to seed it from the process ID and the system time in microsecond, but the problem is both of those are relatively predictable values, so it didn't really have that much entropy, and it wasn't that hard to try values until you'd guess it. This one was quite a surprise. I remember this coming out in 2012. Someone just took researchers just got all the public keys from all the HTTPS sites on the internet and just checked them mathematically to see if they were using the same prime numbers, and a bunch of them were, like 4 out of every 1,000. A lot of them. And said, how is this even possible? There was a huge argument for a year or two, what could even cause this? And what they finally found was it comes just from the random number generator. What happens is, when devices boot up, they reach a point where they generate something, but you have a whole bunch of identical devices like firewalls with the same hardware, the same clock speed, the same everything. And when you boot them all up, a bunch of them are likely to create this at exactly the same microsecond and get the same number. So the lack of actual randomness means that, even though with RSA keys of 1024 bits long or something, there should be no chance that you'd ever find 2 of them the same, you will when there's no randomness in your random numbers. So then there's MediaWiki, used to Wikipedia, used an unsecure random number generator in it, which older software often made that mistake. And CryptoCat was a notorious chat client created on the Arab Spring. In the Arab Spring, which was 2011, 2012, all these people in Arab nations rebelled against their government, and they organized protests, and it was illegal, and the government would arrest them and shoot them, and they organized them mostly on Twitter. And it was very unsafe. Twitter was not encrypted or anything, it was public, and so the available encrypted message clients at the time were hard to install and hard to use, so they invented this thing called CryptoCat, which was an encrypted alternative to Twitter and easy to use. But it was written badly and had a lot of flaws. And so anyway, it wasn't as good as it should have been because the code just had sloppy mistakes in it, although they updated it later. And the developer said it's a whole lot better than using Twitter, which is the real alternative, which it probably was. But anyway, a lot of people got very upset that its cryptography was substandard. Anyway, so let's try another Kahoot. Good, so I made a Discord for these classes, that's good. Let me make a note. After the Kahoots, I'll put it on the news or something. I'll try to post the invite link in Sam's other Twitch streams. Yeah, share the link, yeah. I'm gonna, yep, I'll put it on my page or something. This is good. There should be a Discord. I got enough social networks, I can't do Discord too. And I think there'll be Discord for the competition team too. We've talked to Liz, I think there'll be one. Anyway. All right, looks like maybe this is all we have. All right, so what item harvests entropy from the keyboard and mouse? That's the random number generator. I think you'll see this if you use OpenSSL to generate a key. It'll say, now move your mouse around or type on the keyboard until you have enough entropy to make your key. Anyway. All right, which item updates the entropy pool? Yeah, the pseudo-random number generator has a few methods that update the pool, which is how it achieves forward secrecy. You keep adding new randomness so the future becomes unpredictable. All right, what algorithm does the Mac use? It's yellow for the Mac, good. And what source of random bits is recommended on Linux? It's urandom. It's kind of obvious. Random was the original name, of course, and that's the old one. And urandom is the improved one. So it's the one that's recommended, the one that doesn't block. All right. I know who that is. Double time winner, good, that's good. And, all right, good, that's also a 2-time winner. Okay, good. All right. So let me stop the recording. And there we go.